All right. Hi, everybody. Thanks for coming out today. I think we're going to be doing a breakdown of GMP. We have Ben here joining us, and he's going to give us a walkthrough on it.
GM Ben.
How's it going, guys?
Yo,
Doing
yo.
good.
Hope everybody's week is off to a good start. We've been, just for kind of updates, we've been checking in with a lot of the teams over this week. We'll continue to do one-on-ones. For those of you watching that haven't yet scheduled a one-on-one, please do so whenever you get a minute. The calendar link, GM. The calendar link is in the Telegram group, so make that easy. And then Ben will sync separately about there are certain projects that might be needing an Axelar one-on-one in the meantime.
Sounds good.
Sweet. Well, with that, I'll hop off the stage. So good luck, everybody.
All right.
Let me get the slides here quickly.
Absolutely.
You know what? Actually, today's going to be a bit of live coding, so I'm just going to share my screen, if that's okay.
Oh, yeah. Sounds great.
Okay. Let's just roll with this. Entire screen. Cool. Can you guys see?
And you are live.
Sweet. Just thinking about, I guess I can't see the questions now. That's fine. Just cut me off if there's a question that you want me answering, or if a bunch accumulate. So welcome back, everyone. As a reminder, I'm Ben with the Axelar team. Welcome back for another session. Brief agenda for today. We'll do a little recap of last week's talk, kind of what is Axelar, how we got to where we are, and then we'll get right into GMP, general message passing. Like, what is it? Why does it matter? We'll go over how we do cross-chain gas payments to actually to pay for GMP messages. We'll go through the step-by-step of a live GMP transaction on the Axelar Scan Block Explorer. And then we'll end with, hopefully, if we have time, for 3 GMP examples. So we'll start with a simple, like, hello world one, sending a string from one chain to another. We'll go through a two-way GMP call, kind of like a ping pong message. And we'll end with an encoded function signature call. We'll do it in the context of, like, sending an NFT. And then we'll do some Q&A at the end. Awesome. So brief recap of what we talked about last week. Remember, if I said there was one takeaway I wanted you guys to have about Axelar, like what it is, what makes it unique, is that it's a blockchain that connects blockchains, enabling universal Web3 interoperability. With the 2 major improvements compared to other interop solutions of, like, scalability and security improvements. The easiest way to view Axelar from, like, a 50,000 foot lens was as follows. Hub and spoke, layer 1, connecting all these different blockchains. We're on 81 chains now, so this table is a bit out of date, but the idea of the hub and spoke visualization is still the same. And that kind of brings us to where we are today. So we have this blockchain for blockchains, enabling interoperability in a secure and scalable way. But what can we actually do with it now that we have this infrastructure set up? And the main or most exciting use case to me is general message passing. So what is it? The easiest way to understand it is that Axelar's general message passing, or GMP as I'll refer to it, enables a developer building on one chain to call any function on any other connected chain. So if we unpack that, we mentioned this, we showed this slide briefly last week. You can send something as simple as, like, a string from Ethereum to Avalanche, like WAGMI, or you can also send, like, a function encoding to actually execute functionality on a smart contract on a destination chain from the context of calling it on the source chain. And we're going to do both of these today. So pretty neat stuff, in my opinion. When we're actually sending GMP messages, there are 2 critical components that we kind of have to deal with. The first one is the Axelar gateway, and the second one is the Axelar gas service. The gateway contains a whole lot of functionality beyond the scope of what we'll actually need for sending general messages. There's, for example, stuff like rotating signers and and then a whole lot of other stuff for like the Axelar integration as a whole with a given blockchain. For the purpose of sending a GMP message, there's only going to be one function which we need to call directly on the gateway, called call contract. So we'll see that in action shortly. The gas service has a lot more relevant functionality that we'll be dealing with just for sending GMP messages compared to the gateway, which is like for the entire Axelar integration. And that really opens a whole can of worms of like, well, we're sending a message from Ethereum to Avalanche. Let's say, how do we handle gas? Like, where do we pay for the gas on Avalanche? What about the gas on Axelar? Because remember, like, Axelar is itself a blockchain which has its validator set that also need to get paid. So the gas service it really exists for all of that. So before we get into the Axelar gas service, we have to understand how gas fees work in cross-chain payments. The first thing we need to understand is that there are two fees. There is the base fee and the execution fee. And the total cost that we'll be paying for cross-chain transactions is the sum of that base fee and the execution fee. So what is it? The base fee is the cost of what's called the confirmation and the approval. The confirmation and the approval are two separate components of a cross-chain transaction. Confirmation is kind of when the validators are coming to consensus about a message that's being sent, and approval is the cost of like marking a message as approved. We'll see both of these kind of jargony terms on Axelar scan when we're actually sending a message from chain A to chain B. But the easiest way to understand the base fee is that it's basically three components. It's the cost of the Axelar validators. Remember the 75 validators of the Axelar layer 1 actually voting on the transaction. It's the cost of relaying the transaction from chain A to chain B. More on relaying in a second. And it's the cost, if there is a refund, if you overpay gas, it's the cost of actually sending back that refund. So that's the base fee. The execution fee is a bit more variable. It's just the actual cost of the gas limit times the gas price of the destination chain. So if we're sending from Ethereum to Avalanche, it's the cost of executing that chain on Avalanche. That's going to be the execution fee. A brief divergence onto relaying. You may have seen this in the doc. You may have heard me mention it. It's kind of a jargony, in my opinion, overwhelming term when people say relaying. All what it really means is that when you are sending a transaction between two chains, there are a lot of steps that would have to be triggered manually by you. Like we have the Axelar validators who are coming to consensus about each message that was sent and kind of handling the security of everything. But the actual process of triggering a message on the destination chain, for example, once the validators have come to consensus, needs to be done by someone, right? Like you could technically manually do it. It'd be annoying to have to manually trigger each message on the destination chain, but it could be done. But the relaying infrastructure that the Interop Labs team has spun up is kind of a complementary service to make the user experience and the developer experience much easier. Relaying is a trustless service. Like no one could maliciously change the data that's being executed on the destination chain, even if they wanted to, because the message is what was signed off by the Axelar validator set. It's literally just something to make the flow of a cross-chain transaction much smoother. So that's what I mean when I say relaying. So what does the gas service actually do? We know that we have a base fee and an execution fee that gets summed together, and that is the cost of sending a cross-chain call. Brief note on my latter bullet point here. There's, in the case of dealing with the layer 2, there's also a base fee, execution fee, as well as layer 1 execution fee. That's because the security of a layer 2 transaction, the way we handle it, is waiting for it to get executed and finalized on the layer 1 chain. So you also have to worry about that cost as well when dealing with layer 2s. But with the whole point of the gas service, beyond abstracting all this, is really for you guys, having a better developer and user experience. It basically allows you to pay for the entirety of the cross-chain transaction in the native token of the source chain. So what do I mean? If you're sending a transaction from Ethereum to Avalanche, you don't have to worry about holding AVAX, assuming Avalanche is your destination chain. You simply have to pay Ether to the gas service on Ethereum, which is the source chain in this example, And then the gas service kind of abstracts everything else away. You don't have to worry about holding AXL to pay the validators. You don't have to worry about holding AVAX to pay the Avalanche blockchain. You just pay Ether and everything gets paid for on its own. That's not to say there's a subsidy per se, like the money is still coming out of your pocket, but or the sender's pocket, I should say, but you don't actually have to worry about holding all these different native assets for each cross-chain transaction you want to make. So that's kind of the purpose of the gas service. Stepping away from that though, now that we actually understand how to make a gas payment, what actually happens when we're making a cross-chain message? It's a very simple process, which can be broken down or simplified, I'll say, in this diagram. Imagine, let's start from the bottom left corner here. We have a dApp on the source chain of Avalanche, and we have another dApp which we deployed, say a game, which we deployed on 2 chains, on Avalanche and on Polygon. Remember the gateway contract, which I was mentioning before, the first contract here? The gateway will expose a method called call contract, which I previously mentioned. Your dApp, all what it needs to do is actually trigger that call contract function in its own logic to trigger that cross-chain call. In addition, one thing I'm kind of omitted from this graph is you also have to trigger the gas service, which we just talked about. So there's technically 2 calls. There's the gas service call and the gateway call. But for simplicity, let's just look at the call contract now. When we trigger this function, we're kind of done on our end. Now the Axelar infrastructure picks up the rest. But just so you know what happens, when you trigger from your dApp this call contract function, the gateway emits an event. The event is then submitted to the Axelar network. This is the layer 1 Axelar, remember this guy right here, where the validators are running. The validators come to consensus about the message that was sent. They then mark the message as approved in the form of a transaction to the gateway on the destination chain, because remember, every chain that Axelar connects has a gateway deployed. Once they mark that message as approved, there'll be another call to your own dApp on the destination chain, which will need to have a function called execute with whatever logic you want built into it. And then the execute function will get called. It'll basically say like, hey, is the message that I'm about to trigger, was it actually approved? Basically checking to see that step 3 was approved. If it was, then you can execute any generic logic you want. So one more time, your dApp imports the gateway contract to trigger this call contract. The gateway emits an event. The event is picked up by Axelar. Axelar comes to consensus about the message, marks the message as approved, and then makes a call to your dApp on the destination chain with the message that was submitted into the execute functionality. And let me see if there's any questions so far. I have a lot of GMT back. And that was a lot to unpack. So I'm actually I think the easiest way to see all of this is by building something out together. We're gonna build a few different applications. We're gonna start with a simple Hello World application. So let me close this out. So we have a contract here called demo. Apologies for anyone working in like the non-EVM ecosystem. I'm assuming most of you guys are in EVM, so we'll stick with this. So we have this kind of starter code here. Don't really worry about the storage variables for now. It's not really relevant to how you send a GMP message. But let's actually start building something out together. So I'm going to hop back and forth between my slides and the code a lot. Remember, GMP, the 2 major components you'll have to deal with is the gateway and the gas service. So in our constructor, let's pass in the address of our gateway and our gas service. They're just 2 separate contracts that live on each blockchain which you connect to. I'm also going to pass in the address of the gateway to what's called the Axelar executable. This is another helper contract which you see we imported along with the gateway and the gas service, which will have the execute function defined. This, remember, step 4 here. So we're going to need that to actually just override the execute function. It interacts with the Axelar gateway as well, which is why we can just pass in the gateway here to the executable. And it's getting mad at me because we need to inherit the Axelar executable. So is Axelar executable? And that's getting mad at me because it wants us to override the execute function. So let me define that quickly for now. In fact, I'm actually just going to click into it. This is the Axelar executable, and I'm just going to copy the executable function signature paste it here and just change virtual to override. And that should make it happy. Okay, and we'll touch on these 4 parameters in a bit. For now, all what you need to know is we have a constructor, which we're going to use to pass in the address of the gateway and the gas service, the 2 major contracts that you need to worry about, or not, I hate saying worry about it, interact with when you're making a GMP call. So let's pass in those addresses right now. The first, the gas service, well, the gateway we already passed in here to executable, which we're inheriting, so we don't have to worry about passing that in. Gas service, we have to still pass in to our storage variable here on line 19. So gas service equals gas service, and I should pass it in as a correct type, Axelar gas service. Okay, let's see if I can still compile all happy. I can, cool. So now we have our constructor where we're passing in our 2 addresses. Now we have access to these 2 contracts. So let's actually send the GMP message, get to what we've been talking about for so long. We have a set remote value function, which we'll use to actually send the message. It's going to take 3 parameters. The first is the destination chain. Where are we going? We need to pass it in as a string. The second is the address on the destination chain. Once we arrive to whatever destination chain, like what's the address we're going to there? And finally, because it's just a simple hello world app, we're going to pass in just a string of a message, kind of like I was doing in this slide here, where we just passed in like a WAGME message. That's all we're going to do for this example. We then need to mark the function as, let me close this. Can I, no, Remix AI Assistance. How do I get rid of this? Go away. And can I close this? There we go. Nice, we can see the whole thing. I need to mark this function as external, and I'm also going to mark it as payable. Why? Because when we're making our call to the gas service, remember what we had talked about before, this gas service, we're actually going to need to send a message value to it. So we need to mark that as payable. Okay, the first thing we want to do here is require now that our message value that we're passing in is greater than 0. If it is not, say gas payment is required, and we should revert immediately if for whatever reason the user didn't send a message value. Next thing we want to do is actually prepare our message to get sent. So right now it's just a string. When we're sending a message via GMP, we're not going to be able to use a string. We have to pass in a bytes representation of our string. So we can generate a bytes object very easily just by calling ABI encode and encoding the message. Awesome. We now have our string, our kind of hello world string in the format that we need. Now let's actually interact with our gateway and our gas service contract, just like we were doing in this diagram. Though here we were just interacting with the gateway, we're also going to need to interact with the gas service. So let's start with the gas service, because the first thing we need to do is pay. So we have our gas service variable in storage, which we set in the constructor. We're now going to call a function called pay native gas for contract call. Bit of a mouthful, but it's accurately named because all what we're doing is paying in the native token of whatever source chain we're sending from. And it's going to require a number of different parameters. Let me actually pull it up if I can do it. Axelar gas service. Yeah, pay native gas for contract call token. It's going to require 5 parameters. The sender, who is actually sending this message, like who's paying for it. The destination chain, where are we going? The destination address, where are we going on that chain? It's basically the parameters that we passed into our function call before. It's also going to require, notice, a bytes version of the payload, which is good because we ABI encoded just before. We're not passing the string. And lastly, the 5th address is the refund address. If for whatever reason we grossly overpay the amount of gas that we're sending to the gas service, it'll refund us the surplus. So we pay native gas for contract call. The sender will be this contract, so address this. The destination chain will be what we just passed in up top as a parameter on line 28. Same with destination address. The payload is line 31, and the refund address can be the message.sender. That satisfies the gas payment. So once we call this, we'll successfully make a gas payment. Then we will need to make our final call to the gateway. Remember this call contract function. So let's do that. Gateway call contract. It's going to take in very similar parameters. Let me add a semicolon here, which is going to be basically same as the pay native gas for contract call. The destination chain, the destination address, and the payload. Awesome. Once we actually trigger this, we will have successfully sent a GMP message. It's literally that simple. You have to convert your message to a bytes type, pay the gas with the gas service, and trigger the message with the gateway. But we're not done yet. We're almost done. Because once we actually send our GMP message, we'll have basically completed this first leg of the graph where we send it. The gateway will then emit an event. The Axelar network will receive it, come to consensus, mark the message as approved. But this step 4, this execute, we haven't actually done yet. It's going to get there and not do anything. So let's actually write up some logic in our execute function. Note we've already inherited it from the Axelar executable contract. Then we can just write up some simple logic. So first we have our payload, which is basically just this payload that we encoded back on the source chain. So let's destructure it to a string payload, basically decoding it from what we encoded it on line 31. We could then actually, let me talk quickly about these parameters. The command ID, don't worry about it really. It's just a kind of global identifier across Axelar, a bit beyond the scope of this talk. The source chain and source address are very handy. These are parameters that we get for free. When the relayer is calling this function on the destination chain, it basically passes in these addresses. So these strings. So the name of the source chain, where is the message coming from, and the source address, where on the source chain is it coming from. So let's just pass that into these storage variables that we defined up top here. So source chain, let me set these as underscores, underscore. Source chain equals source chain, source address equals source address, and payload we've already done. And we can then emit, we defined an event up top called executed. So let's just emit it to make sure everyone's happy. Source address, and the message. Remind me what we had up here. Yeah, the from and the message. Cool. And that is basically it. This is the entirety of our hello world. This would be here. The entirety of our hello world contract. We call this, sorry, let's start from the top. We have this constructor. We pass in our 2 key contracts, gateway and gas service. We trigger this set remote value function, which takes in the destination chain. Where are we going? The destination address, where on that chain are we sending to, and the message. What is the actual hello world message that we're passing? We encode it to bytes type. We pay for the gas with the pay native gas for contract call function, and then we trigger call contract to actually send the message. Let me see if this now compiles, and let's actually try deploy this guy and see if we can get it to work. And bear with me for the Murphy's Law of live coding. Injected provider demo. Okay, cool. So gateway, we need to pass in the gateway address. All of those should be right here on our docs. So if we're going to be deploying it on Binance, for example, we can pass it in gateway and pass in the gas service. So we deploy one instance of this contract in my Binance. Yeah, on Binance. I'm just gonna log it right here for myself. Binance instance of this entire contract. And now let's do it again on Avalanche. So we'll have 2 instances of this contract. Where is Avalanche? Right here. If I can afford it, I hope. I think the gateway address on Avalanche is different. So let me make sure I grab the correct gateway and gas service on Avalanche. The gas service is the same. The gateway is a bit different. So let me deploy now on Avalanche. Awesome. So now we have 2 instances of this contract, one on Avalanche and one on Binance. I'm going to pause right here to see if there's any questions. Could GMP be hypothetically used to do KYC verification for a client if their wallet address has already been KYC'd on a different Axelar connected network? That is a great question. GMP, think of it as simple as, could you do it between two? Oh, could you implement this between two contracts on the same chain? So if you're doing KYC with, I don't know, something like chain analysis, and that it involves, reading from a list of addresses that they have, in theory, yes, you could do that because you're just sending the list of addresses between chains. But you really have to unpack that a bit more, like how you're doing the KYC to begin with. But think of GMP as interacting between two contracts on different chains, as simple as interacting on the same chain. You can pass arbitrary data and messages, so you can do whatever you want in theory. Oh, okay, thanks. Answer the question for me. What plugins do you recommend for Remix when building with Axelar GMP? In general, I don't really use Remix when actually building with Axelar GMP. I go more on VS Code. Remix, I think, is great for these sort of demos because it's the rawest form of interacting with everything on chain. Yeah, so I can't say I really use it that much. I'm more of a, well, I guess Cursor nowadays, but I more when I'm actually building stuff, I'm going off of Remix. I just think it's most helpful for these demos. So let's actually see this in action now, and we're gonna go a bit over time here. But I'll try to go through this quick. So we have let's send a message from Binance to Avalanche. Actually, Avalanche to do Binance to Avalanche, just because I don't have as much money on Avalanche. So Binance testnet. I'm going to pass in the address here. I'm going to call set remote value, pass in the name of the destination chain, Avalanche, pass in the destination address, which we wrote down for ourselves right here, and the message, hey, from Binance. Now I'm going to call this and it's going to fail. Why? Well, remember this require statement. We actually have to send a message value to the gas service. So let's send in some way here. 1, 2, 3, 4, 5, 6. I sent in 0.1 Binance native tokens, whatever their native token is called. Awesome. We have sent this transaction. I can now see it on Binance. Oh, I need the testnet BSC. There we go. I can see it here, actually executing on Binance. I can see the logs for native gas paid for contract call. Remember the function that we had for the gas service. I can also see the contract call function getting emitted. This, recall, is the really important event that gets emitted by our gateway, which eventually gets picked up by our relayer and submitted to the Axelar network. But it would be great if we can actually see the whole 50,000 foot view of the transaction. Fortunately, we have our own block explorer. Remember, Axelar is a layer 1 in its own. Really, really cool website to see like the kind of most up-to-date stats on Axelar. This is, you could tell, a much more up-to-date graph than the one I shared on the slides with only like 10 chains being connected. But not to get too off track, all I have to do is paste in the transaction hash, insufficient fee. Fortunately, from Axelar Scan, I can actually add extra gas from the Explorer itself. We also have a JavaScript SDK where you can do all this programmatically. So gas payment was sent. What's really neat is I can actually see everything on the native Explorer as well. So I can see the first 2 steps of this transaction, which is the transaction being sent, the gas being paid. I can click on this and it takes me right to the native block Explorer itself, which is the same hash as we had open before. Currently, we are going through the confirmation step, which is the Axelar network now waiting for finality on the source chain. On Binance, that's pretty fast. And now actually doing that whole voting process that we talked about so many times already, like the 75 validators now coming to consensus. So that's what they're doing right now. Once this actually gets executed, I'll have a hash here. There we go. For the Axelar chain itself, notice the logo here has changed. Make it a bit bigger. We're no longer on Binance. Now we're on Axelar. I can click on the poll ID to see the votes of all the different validators. says it's still pending here, so that vote is happening right now, but momentarily we'll see all these validators coming to consensus. I don't think it's only 34 rather than 75. It's because we're on testnet, not on mainnet. On mainnet, that'll be a lot more validators than just this. So now we've confirmed. Now we're sending this fourth leg of the transaction, which is actually marking that confirmation as approved. So this is actually going to be done on the destination chain momentarily on Avalanche itself. And then the final step will be to actually execute that transaction. While this is going, I want to step through our other two examples very briefly. I apologize. I know we're a bit over time, but I think it's cooler to actually see like more live examples going through. And we'll return to make sure that executed momentarily. So that was our demo 1. Demo 2 is a different example. You'll see it's very straightforward. We're not going to write it all together. But it's basically doing the same thing. So we call set remote value. We send the message with pay native gas to contract call and call contract. The difference is on our destination chain, we're going to deploy a separate contract. We're not going to deploy the same contract twice. On the destination chain, our execute is not going to just write to storage. Well, I guess it is. What we're also going to do is actually trigger call contract again. And what does that do? It actually sends a message immediately back, basically a callback immediately back to the source chain. So we're going to kind of have like a more ping pong transaction. Just for time's sake, I'm not going to run through this one and deploy it. It's going to be exactly the same thing. But the callback is going to execute automatically. And when it's done, it's going to look something like this. So we trigger from source to destination, gets executed. And then we have a two-way call actually going from Avalanche to Binance. Let's see if our first call actually went through. Nice. Our call that we did together has now executed. So if I click on this execute function, I will actually see in our events, pay from Binance message coming in, which is what our contract, if you recall, emitted. I already closed the demo 1, but it's what it emitted when it executed on the destination chain. So we know that the cross-chain transaction actually worked. I'm going to go through 1/3 demo very, very quickly, just because I know we're over time. This is now we're off Freemix to address the other question. This is actually in our Axelar examples repo. It has a whole bunch of really helpful examples, including the 2 I just showed you. We're going to look through the multi-chain NFT mint example. Let me make it a bit bigger. This example consists of 2 contracts. The first is a super simple NFT contract that I made. It just inherits from OpenZeppelin's 721 standard with a safe mint function. In this contract, what it's going to basically do is it's going to mint that NFT from the source chain. I'm going to call it like from Avalanche, and it's going to mint an NFT on Binance. We're going to do this not on testnet. We're going to do this in the context of this examples repo, which is basically running just like a local hard hat environment to kind of simulate blockchain executions. So let's actually go through what is going on here. This should all look pretty straightforward or familiar at this point. In the constructor, we pass in the gateway and the gas service, just as we did before. We're also passing in the address of our NFT token. We then have a function which will actually send the GMP message and a function that will receive the GMP message, the execute function. Remember, this execute has to be very specifically written out because it's being inherited from the Axelar executable. On our mint on destination chain, we have the same require function that we did before. And then instead of ABI encode, we encode with signature. Why? Because what we're doing is actually encoding a raw function signature. The function signature we're encoding is safe mint. This is just straight from the NFT contract itself with the 2 parameters that it expects, like address, like what is the receiving address, and the UN256, which is the token ID for the NFT. We then pass in the actual value of these 2 addresses, so the address and the token ID. We then go through the same 2 steps that we did before. So pay native gas for contract call to actually pay for the entire transaction with the same parameters as before, except the mint NFT payload is different than the hello world payload that we did before. And then we trigger the call contract function, same as we did before. And on the execute function on the destination chain, all we have is just a generic solidity.call function, which can execute the generic function signature that was passed in. And that will actually mint the NFT on the destination chain. This by no means is like the recommended way to send NFTs. It's just a simple demo kind of showing the flexibility and the power of GMP to actually be able to send more than just like strings between chains, like saying hello world. We can actually send full-on function signatures with values all encoded into the same bytes object to actually have these generic executions. So we have, let me actually spin this up with you guys here. If you guys have checked out the Axelar examples repo, you just have to run npm run start, which will fire up these simulated blockchains. Then I want to deploy this this contract on our simulated chains. So for that, I can run npm run. I think it's, let me just check the README. Right off the top of my head. Yeah, npm run deploy EVM multi-chain NFT mint local. I can also run this on testnet if I wanted to. I'm just going to do local because it's quicker. Awesome. This now deployed this multi-chain NFT contract on all these simulated blockchains. And now to run the example, all I have to do is run npm run execute EVM multi-chain NFT mint. That's the name of this example. We're going to run it on our local environment. The two simulated chains are going to run it from Avalanche to Phantom. The receiver will be me. I'm just going to pass it on here. And then the token ID is just going to be like 3. And hopefully this works. So the balance right now for my token ID 0 on Phantom is 0. And after I run it, the balance is 1, which means we have successfully minted our NFT. And this is all being done in this script right here, which we have, which is basically logging the balance of function on the NFT on line 28 here. We trigger the mint on NFT destination function right here, which we wrote up in our Solidity. So we trigger that, we pass the destination name, the destination address. We then, after a loop, waiting for this balance of to increment, just log the output of the balance of function again, which we can see being done here. So we can see in this example that we have successfully executed a mint function by passing in just the function signature via GMP. So there's a whole lot you can do here with GMP. Another example, which we'll talk about next week, is ITS. ITS, our interchain token service, is doing something kind of like I just demonstrated here. It's just calling the mint on ERC20s the way we were just kind of doing with our NFT example, which is obviously in a much more robust way. But really NFT is kind of the base layer of not NFT, GMP is kind of the base layer of everything which you can do on Axelar. It's really, really cool stuff to play around with. And that is all I have for today. I'm going to jump to those questions quickly. Again, I'm going to leave the QR codes up for our Axelar examples, which I just referred to before. You can check them out right here. For some helpful GMP videos, walkthrough, you can scan this right here for our YouTube examples. And that is all I have for today. Let me check some of these questions. A way to trigger, minimize the transaction fee. The transaction fee is it's, remember we were talking about it before, there's the base fee and the execution fee. A lot of it is variable depending just on the current gas price for a given chain, right? So it does fluctuate. It's not fully in our control. And then for the Axelar side of things, like executing on the Axelar chain is very, very cheap. I think it's like, we have a hard-coded value of like 0.2 AXL, which is like pennies, for just like triggering the vote on the Axelar chain. Yeah, when it comes to ping-ponging and overall message passing, do we need to pre-compute the gas manually, or does the gas service? Yeah, great question. So about the cost of executing. So the gas service does not actually calculate the cost for you. It was something the team was working on, like on-chain gas estimation on the gas service. So it might be a little unclear because you might see those function signatures there. that is something it's really on a need to use basis. If you do need to actually calculate the amount of gas being sent, I strongly recommend we use our off-chain gas estimator via our Axelar JS SDK. I can share that. It's in our docs, like how you do that. There's a function called like estimate gas fee, if I recall correctly, and you just pass in like the source and the destination, and it'll calculate the gas cost for that certain time. If you don't even want to worry about that, you can just pass in a generic amount of gas, like a kind of buffer price, like I was doing in this example. I just passed in like 0.1. And then the gas service will refund you the difference. So you don't really have to worry about overpaying because you get refunded anyway. Yeah. And yeah, I'll send that. Let me find that doc for you. Join chat. Oh. See if it lets me send it here. Continue. Oh, having trouble connecting to my YouTube account. It's not going to let me send it, but I'll send it in the Telegram chat right now. Can you control the speed of transaction to reduce speeds? So yeah, great question. So speed is determined by a number of factors. Sorry, I'm just sending that link for our docs. I just left the link for the docs on transaction fees in our technical assistance channel. Yes, Louis, to answer your question, transaction fees speed is determined by a lot of factors. The most critical one being finality time on the source chain. So I chose on purpose 2 very fast chains just now, Binance and Avalanche. If I were to have gone on Ethereum, the finality time would be a lot slower. The reason for that is security. Like imagine a scenario like where we execute something that alters the state of a contract on the destination chain, but like there was a reorg on the source chain and we just bypassed that finality. We didn't wait. Right now you can have contracts that are out of sync with the reality of the source chain. So that's why we kind of take a lot of precautions and waiting for finality on the source chain before executing on the destination. There is a service called Express that has existed in the past specifically for the case of sending ERC20 tokens. So that could be something where you skip finality on the source chain. You're taking a risk by doing that. It's good for low value transactions. So what it does, it's like you loan out 100, let's call it USDC on the destination chain. So it's executed automatically. And then when the transaction finalizes on the source chain, then we pay back the loan, or the relayer rather would pay back the loan to the source chain. Yeah, so that's a service that's been used for ERC20s. It's being worked on to get integrated for all ITS integrations as well. But right now, speed is largely determined by finality of the source chain.
All right. When we give just a second to see if we have any other questions come through. I might have missed it, but did you get this one here?
Answer my questions above for security.
Which was about, his question was about ping pong.
Do we need to pre-configure? Oh, great question. Yeah, so for the kind of, the callback transaction, the ping pong as you called it, you don't need to pay gas twice on the destination chain. So if you look through the examples where we had it before, you'll notice that all what we did in the execute function on the destination chain was trigger call contract on the gateway. We didn't actually trigger the pay native gas for contract call a second time. The relayer is kind of smart enough to pay for the transaction on the second leg on its own. So that's actually a great call out. Actually, it'll be an error if you try to pay gas again. So good question there.
And then we got one more from Louis.
Is it better to have, I mean, it depends, right? For the sake of the demo, absolutely. That's why I did Binance right now instead of Ethereum, because it's faster for demo's sake. But if you want to be on Ethereum, for all the great reasons there are to be on Ethereum, like that shouldn't be a reason, in my opinion, to not go on Ethereum just because the finality time's a bit slower. So especially if you're doing like an ITS integration, we'll have Express there at some point. So yeah, it is faster on Binance to have it as a source chain. But but I wouldn't just dismiss Ethereum as a result. Same for the layer 2s, also have a slower finality time.
All right, that's all for the moment. We'll give them just one more moment because we actually do have till the top of the hour on the schedule, unless you
Sorry?
peel off. Oh, sorry. We actually do have till the top of the hour on the schedule.
Oh, okay. Okay.
Yeah. So unless you specifically need to peel off.
All good.
And then we got one more here.
From if Ethereum is your source chain, then when you're sending a cross-chain transaction, yeah, it would take the finality time of Ethereum. It's not always 15 minutes. Actually, the easiest way to see it, if you go to, I think we talked about this last time actually. If you go to Axelar scan statistics, can I share my screen again? Yeah, share screen. If I go to this page right here on Axelar scan, with all the interesting stats about Axelar scan, I scroll to the bottom, you can see here the GMP time spent on each chain. So you can see, for example, C is the most important one, like the confirmation time, it's like the finality time. On Binance, it's only like 17 seconds. If I go to like Ethereum, it's 16 minutes, right? And you can kind of see this for each of these chains. Like Polygon will be 45 seconds, Optimism will be 29 minutes, because we also wait for the transaction to get finalized back on layer 1 for any of these layer 2s, to really be precautionary when it comes to security. Avalanche is 20 seconds. So yeah, this is a good page to check that out. And you can also, I guess, just to really see it in action, I'd recommend go to Axelar scan and just filter through transactions to kind of see, like previously, how long they've taken really with Ethereum.
One more coming through.
Any suggested best trust? That's something you could do. It really depends what you're trying to do. I'm not familiar with how Layer 0 has trusted apps, but it's something you could do, because remember, in the execute function, there is the source chain and the source address, which you kind of get for free as parameters. So you can leverage those to kind of set blacklisted addresses, or like require it to be a whitelisted addresses that that's sending the cross-chain call that you're receiving. So it's definitely something you could do. Yeah.
Okay, well, excellent. We can probably call it there. So thanks so much, Ben, for walking us through that. And thank you, everybody, for coming out. If you, as always, if you have any questions for Ben or for the Crack Labs team, you can ask in the Telegram. We got channels for that. And remember, everybody, to set up a one-on-one call. We got links for that both in the Telegram and in the handbook at the bottom of the page. And you want to make sure you do that so you can check in on your progress, know what's happening with your project, and make any suggestions for how to best prosper inside of the program. Outside of that, check your calendar for the other upcoming events. And if you want to revisit anything that was said here, rewatch it, the link for this will be posted both in the handbook and in the Telegram, so you can watch back at your leisure. Other than that, thank you, Ben.
Thank you. Thanks for having me. Have a good one, guys.
All right. Everyone have a good one.